Hello, good afternoon. Am I audible? Can anyone please confirm? Amrita, Gopan, Heath, Sagar. Okay, good. We'll wait for a couple more minutes for other people to join. In the meantime, if you have any doubts, you can ask. I'll try to address them to the best of my abilities. Otherwise, we'll wait for a few minutes so that other people can join and then we'll start a second session. So I'm muting myself. If you have any doubts, please go ahead. I have just now shared my email address, that is learnwithamitbansal@gmail.com, in the chat box. I have also shared the YouTube channel on which I upload the live recordings of the sessions that we conduct. So I have already uploaded the first session that we had conducted. Before I start for today, I'll go through a brief revision of very quick recap of what we had done the last week, and so that we can continue to be more streamlined, easier to understand. That's the idea. So as always, feel free to stop me anytime with the topic that we are discussing. And before the class, like I'm waiting for a couple more minutes. If you have any doubts regarding your assignment which you have submitted, assignment 1 that is, or the previous session that we have conducted, or as I know, the week 3 content is also live. So from week 1 and week 2 contents, if you have any doubts, you can ask. Feel free to ask. I've shared my email ID so that if you want to send some conceptual doubts, forum is the best place to ask a doubt so that other people can also learn with you and understand. But if you feel that you need to talk privately, then feel free. I've shared my email address, and yeah, so that's that. Now let's begin today's session. uh, is my screen visible? Just confirm the presentation, that is. uh, Please either write in the chat box or speak up that is my presentation visible. Introduction to Semiconductor Devices. Okay, thank Ritik. All right, so that's that. Now we'll get started. Hmm, let me open my presentation. Yeah. So again, good afternoon, everyone. Welcome to the problem solving session for the course NOC 23 EE82. That is Introduction to Semiconductor Devices, being conducted by Professor Naresh. And this is week 2. My name is Amit Bansal. I am a PhD scholar at IISc Bangalore, and so I work in the fabrication of semiconductor material called gallium nitride. All right, so let's firstly just a quick overview what we went in the last session. If you recall, first we have talked at length about the material classification. By that I mean what property makes a semiconductor or a metal. So we saw that various ideas were proposed, like the presence of free electrons, valency, and all that. And we restricted our discussion to only the conductivity part. That we are concerned when we talk about material classification here, we talk about only the conductivity. We are not perturbed about other aspects of a material. Only the electrical conductivity is the thing that we talk about. Conductivity. This I is not here. All right, and then we saw a bit about the quantum mechanics, some very basic quantum mechanics, that is, in terms of, we saw de Broglie wavelength, and we learned that the quantum mechanics that we are talking about is applicable only where we are in de Broglie wavelength regime. And can someone recall the formula for de Broglie wavelength quickly for me? Anyone? The expression for de Broglie wavelength. Come on, speak up, fellows. Anyone? Okay, it's fine. It's all right. I'll keep asking such questions and hope that you respond. Okay, so the de Broglie wavelength, as we saw, was h by p. Is this correct? I hope it is. Or alternately, we also saw that p can be written as h cut k, where h cut is nothing but h over 2 pi. H is your Planck's constant. So there are two forms that we saw of this expression. This lambda is the de Broglie wavelength that we are talking about. P is the momentum of the particle of which we are associating a wavelength. So is a wave particle duality involved. Also, we saw the expression for Heisenberg's uncertainty principle. Essentially, in quantum mechanics, nothing is certain. Everything is probabilistic. So we cannot say with extreme certainty that this is the position, this is the momentum. Hence, the uncertainty comes into picture. You saw the expression. Finally, we went into quantum mechanics and solved some problems like for infinite quantum wells. If you recall, these were the infinite quantum wells. So I'm drawing the potential here. So this is infinite potential, this is potential, or you can say energy equal to 0, and we saw what happens to a particle, which is what energies it can take, and what is the wave function. The wave function determines the probability of particle being at specific position or having a specific momentum. So we saw infinite quantum wells. This is an asymmetric well where this is the x direction, this is x equal to 0, the vertical wall, this is x equal to L. For symmetric, we have at minus L by 2 and L by 2. Secondly, we saw a finite quantum well. By that I mean we have something like this. So this is V equal to 0, and let's say this is some finite potential V equal to V naught, and some particle is coming like this. Classically, this particle can never be present here. The probability of finding a particle in this on the right side is 0, on the right side of the barrier. That's not so quantum mechanically. So it can so happen that it can tunnel through this. So it has some probability of finding here. And finally, coming back to the topic of semiconductors, which we started in the origin, in the first place. So we saw that semiconductor, how does a band gap even arise? So we saw the dispersion relation. So E versus K. This is known as the dispersion relation, by the way. So these terms keep coming over and over again. Hence, I'm repeating that. E is energy. K is your what is called wave vector. This is the K. This is related to momentum by this formula. So formally, K is known as 2 pi by lambda. Lambda is again your de Broglie wavelength. This K is a wave vector. It's the same as this E versus K. We saw the relations, and we saw that it was a bit involving in that we saw the energy split and so on. I'll again revisit it a bit. And finally, we saw that since there is a band gap, we can so there is a electron valence band, what we call it a valence band, which is full of electrons. It has plenty of electrons. On the other hand, we have a conduction band which has few electrons, but only the electrons present in the conduction band can contribute to the current. So we'll see that how to send electrons, or how do electrons travel from valence band to the conduction band. So we'll try to visit that concept today. We'll again, because this is important, this is the most fundamental part about the semiconductor. All right. So excuse me, people are joining, so sorry about the pings. All right, so now let's move forward and let's come to the first question for today's session. All right, before I start, you want me to repeat something, or you have any doubts in any of these things that we had talked about the last time, or for that matter any topic from week 1 of the course? I can understand that quantum mechanics is sometimes it can get overwhelming, especially for people who do not have who do not have an interest or background in quantum mechanics or quantum physics, especially for first year or second year students from electrical engineering, electronics, or communication engineering. So I understand that, and hence this was only restricted to our first session. Even if you see our not first session, even the first week only. So that's how we restricted ourselves to. So and anyways, I'll be covering the semiconductor portion again today. But if there are no doubts for the quantum mechanics part, let me move forward. All right. So here it's a very straightforward question. It says that photons of wavelength lambda a and lambda b, so there are two photons with each of their own respective wavelengths, and what we are doing is essentially we are these are being incident on a thin gallium arsenide substrate. So if you recall that we talked about semiconductors in the last class. So if you recall your periodic table, right? So there is a group 4, right? Carbon, silicon, germanium, and so on. And on this is your group 3, which is boron, aluminium, gallium, indium, and so on. On this side is a fifth group, which is your um, mm, I'm forgetting the fifth group. Can someone recall what's the fifth group? Group 5 of periodic table. Come on. I'm not asking you to solve a problem this time of quantum mechanics. Just asking what's the group 5. Come on, what's the first element in group 5? Nitrogen. Then we have phosphorus, and we have arsenic. So usually what we find is that the group 4 elements are, yeah, phosphorus. So nitrogen, phosphorus, arsenic, and so on. There are other elements also. I'm not going deep into that. So first we find is this: we know that silicon is and germanium. These are semiconductors. These are also called elemental semiconductors, right? But we can also, given certain properties, some 3-5 groups also can make semiconductors. Like you can join gallium and arsenic, so it will form gallium arsenide is a semiconductor. Similarly, gallium and nitrates. Gallium from group 3, nitrogen from group 5. It's called gallium nitride. So these are called binary semiconductors. You can clearly understand binary means means two. There are two elements involved. I work on this semiconductor gallium nitride, my PhD work. Okay, now we'll go ahead. So that's that. Now what we say is that this is a semiconductor with a band gap. EG stands for band gap, and we have to choose the correct option. Okay, so what means is that, what does band gap mean? So this is your valence band, which you denote by EV. This is conduction band, which you denote by EC, boundary of conduction band. So here there are many states available for electrons. Here also there are many states available for electrons. But this is the forbidden region. Electron cannot reside in this energy state. This is EG, the band gap. In this case, for gallium arsenide is 1.4 eV or 1.42 if you want to be more precise. We have to choose the correct option. So on this substrate, right? So this is a piece of material, you can say, of gallium arsenide, and I'm shining light. So I want to see which light is absorbed. Lambda A will be absorbed, lambda B will be absorbed, both will be transmitted, and so on. Okay. So let's first quickly look into the, I told you I'll revise the band gap in a semiconductor. So what we saw is that, so let's assume there are just the two atoms in this lattice. Lattice is nothing but an arrangement of, in this case we are take the case of silicon. So two silicon atoms, what happens when you bring them close together? What happens is that, so silicon will have its own electric field, this atom, this nucleus, as well as this nucleus, so they will overlap. So what happens is that, so you can see on the x-axis, this is r is the distance between two consecutive silicon atoms. That's on your y-axis, right? A0 is the distance at which they are typically found. This is also known as the lattice constant. And naturally what we find silicon is what is called lattice constant, that's A0. And we see that as you bring closer together, this means as you come here. So if you recall, silicon will have 1s2, 2s2, 2p6, 3s2, 3p1 electrons. Forget about these inner or core electrons. Focus only on the third quantum number equal to 3. So we have what? 3 electrons, right? But sorry, 3p2, not 3p1, 3p2. But we can have at most 6 electrons. So what we have is, we have total 8 states. 2 from 3s, 6 from 3p, which it says here. In 3p we have 6 n states but only 2 n electrons, right? And in 3s we have 2 n states and 2 n electrons. But when you bring the two silicon atoms closer and closer together, you will see that 3p and 3s tend to overlap, and you form a continuous band like this. So you form many energies like this. So gray region is where you have energies possible. So this is also not this, not the first one, sorry. So not this one. And as you can clearly see, this region, I'll choose a different color to illustrate what I'm talking about. The region in green, this region, you find no electronic state is available. This means electron cannot reside, electron cannot have this much energy or this much energy or this much energy. This is forbidden. This is the same, and we represent this in this manner. This is the valence band, also known as EV, conduction band known as EC. Note, it's filled from above. So electrons can be here in the gray region. Again, electrons can be here in the gray region, but not in the white region. That's why it's called the forbidden gap or the band gap. So these are the two bands. This is completely filled till infinity, and same goes for the, actually not till infinity, but it for considerable amount of energy this is filled. Similarly, for considerable amount of energy this is also filled. Okay, so that's the band gap that we had talked about. Now what do we do about it? So we know that gallium arsenide, so here I told you, so here there are many electrons. So there are many electrons. This is full of electrons at room temperature. But here there are few electrons, only very few. Why few, we'll see in today's class, where there are few electrons here. But just trust me that there are very few electrons here, and this valence band is full of electrons, and I'm talking about room temperature. What is the temperature for, what is the room temperature? Come on, room temperature. I am audible, right? 300K, yeah, good. Okay, so we have 300K as the temperature. Very good. So 300K, this is how the picture looks like. But let's say I want more electrons here. Okay, so what do I do? There are different ways in which I can, so here there are many electrons available, but here only few. So what I want to do, I want to transport an electron from here to here. How do I do that? There's a very simple way of doing that, and that is shining light. So let's say I shine a light, which is a photon. Light is nothing but a stream of photons. I shine a light of wavelength some lambda, and similarly consequently an energy E. So how are the two related? Can anybody tell me? How is the energy of a wave of a light and the wavelength of a light related? It's a very famous expression. Can speak or write, it's fine. If you don't feel comfortable talking, just a second. Anyone? All right, I'll go ahead. So E is hc by lambda. This is for a wave. E is the energy of the wave, h is the Planck's constant. Yeah, Kamaljeet, if I'm, yeah, so Ranjani said hc by lambda. What you're talking about is the energy of a particle, p square, E equal to p square by 2m, which we saw in the last class for electronic energy. What it is, it's p square by 2m. Here this is a wave, stream of photons, hence it's E equal to hc by lambda. All right, so what will happen is that, okay, so let me just erase the part on the right so that we are clear. All right, so what I want is that, so on this semiconductor, on this piece of semiconductor which is kept at 300 kelvins, I'm shining light with energy of called E photon. So if E photon is larger than this band gap, what will happen is that an electron will gain some energy, all right, and will go here. This electron will be transported from this to this side. This is called excitation across band gap, the title of this slide. What we are doing is that we are exciting, this electron is sitting very pretty here in its valence band, but we excite it by shining some light, and it goes into the conduction band, and then it can contribute to the current. So when E photon is greater than or equal to Eg, so it has to be at minimum Eg, then it will be absorbed. It will be absorbed, and all the energy of the photon will go into exciting the electron, and some might be transferred into kinetic energy also, but we are not concerned about that here. We are only concerned that what happens if we excite when we shine light. All right, that will happen. What happens in the other case, when the energy of this incoming photon is less than Eg? So even when you shine light, which I show in a different color now, in blue, so let's say this is this case, second case. So in this case the energy is less, so electron energy can be only this much, but this energy is not even allowed. Remember, this is the forbidden gap. So energy can be in the gray region only. Electron can reside only in a gray state. So here nothing will happen. This photon will not be absorbed. It will be transmitted, right? So transmitted mean, absorbed mean it will appear dark to the naked eye. Not to the naked eye, to this wavelength, and this will be transmitted. This wavelength will be transmitted. And as we talked about, that E equal to hc by lambda for a wave. In this case, this photon I am talking about, right? So E photon equal to hc upon lambda, that one, right? And we saw in the last class that the wavelength is related to the energy of the photon. You can just, this is expression I derived, just you can put the value of h 6.626, yeah, 10 to the power minus 34, c is 3 into 10 to the power 8, and you can arrive at this expression. This is nothing, this is just simple rearranging of the terms we saw in the last class also. So what I'm doing here is, since we are in usually we don't talk, when we talk about wave, we talk in primarily in terms of wavelengths, not energies. So hence and this is the discussion we had in terms of energies. So I'm just converting energy to wavelength. So this is the expression, right? So you can see they are inversely related. So when E photon is greater than or equal to Eg means absorption. This means that when lambda photon is less than or equal to lambda g. What is lambda g? Lambda g is nothing but energy corresponding to Eg. So I can define lambda g like this, that lambda g is equal to hc by Eg from this expression. Just put g subscript here. Okay, so when E photon greater than or equal to Eg is absorption, this means when lambda photon less than or equal to lambda g will be an absorption again. Similarly, if E photon is less than Eg, it's transmission, but that means lambda photon must be greater than lambda g. Why this? I told you this inverse relation comes because lambda and E are inversely related. All right. So this is the basic part. So if you shine a light of energy more than the Eg, then it will be absorbed. Otherwise, it will be transmitted. Simple. So here, what I will do is first in this expression, I'll try to derive what is lambda g. So lambda g is nothing but I'll use this expression 1.24 upon E. Okay. So this is hc upon Eg. I write this expression as 1.24 upon Eg. Note Eg we have to put in Ev. Okay, so 1.24, this will be, units will be micrometers, and Eg is 1.42. So let me get my calculator. Yeah, found it. So it's 1.24 divided by 1.42. This is coming out to be around 0.87 micrometer, or you can say 870 nanometer, just change of units. So we saw that when lambda photon is greater than equal to, is less than equal to lambda g, this means absorption. Okay, so what is a lambda photon? Lambda a is 620, right? So lambda a is 620 nanometers, which is less than equal to lambda g, which is 870 nanometers. Hence the first one will be absorbed. This will return in absorption. Lambda b, which is 900 nanometers, it is greater than lambda g, which is 870 nanometers. Hence this will not be absorbed, this will be transmitted. So lambda a will be absorbed, lambda b will be transmitted. So option is this one, option B, this option. All right. So I'll pause a bit here. If you have any doubts or comments, please feel free to speak. I'll just first revise. So we saw that. So this is the summary. So when a photon falls on a semiconductor material, it can excite the electron from valence band to conduction band. However, for that to happen, the energy of photon has to be at least Eg. It has to be at least Eg, and that's what we write here. E photon greater than or equal to Eg means absorption, and correspondingly we see lambda and E inversely. Lambda, this wavelength of the light and energy of the light are inversely related. Hence we come about with this expression, and then finally we just obtain the lambda corresponding to the band gap, and we simply find out what's lambda a and lambda b and compare them with the lambda g. So we see this expression. So any doubts or comments, please go ahead. All right, if no, then we'll go ahead. So the next big concept that is usually involved in the okay, hold on a second. Yeah, So next concept that we usually talk about in semiconductor physics is the what is known as effective mass. So I'll quickly just run through what do we mean by that. So this is a question, we'll come back to that, but first let's have a quick look at the effective mass. So Newton's second law says that F equal to mass into acceleration. Now I have a couple of questions for you. What is this F? What does it mean? Is it external force, internal force, total force? What is it? Internal, external, total? What is it? M naught, I'm taking it to be the mass of electron. So this is an electron mass. A is the acceleration. Can anybody tell me what is this F? Is this F total, internal, external? What is it? Come on, keep a guess. Take a guess. It's fine to be wrong. It's okay. You learn that way. Don't be shy. Any guesses? Is it internal, external, total? Okay, it's fine. I'll go ahead, and so what we have is, okay, periodic field. No, I'm talking about the F is here is force. Newton's second law, force equal to mass into acceleration. I'm talking about that. This is not field here. This F stands for force in this case. So F here is the total force, F external and plus F internal. So the next question arises, what do we mean by F external? So F external, you can just simply imagine that you have a piece of semiconductor and you are applying a battery to this, some external battery of some, let's say V naught. So this will create an electric field, right, which we call in this case as E external. So this will apply an E external across this positive terminal, negative terminal. This is an E external field that is being applied by some battery. So F external will be Q times E external, where Q is the electronic charge, 1.6 10 to the minus 19. Similarly, there will be some internal field. Why will there be an internal field? If you recall, in the last class we have talked about Ronick-Penny model, in which, to put it simply, it's just that electron is not free. It's moving in this kind of a periodic potential. This is potential 0, this is some potential V naught, and the electron has to live in this lattice. Electron is not free. All right, so that's what we had seen in the last class. Option A is correct for last problem. Okay, let me see. Why is that? Why do you say that for a Ranjani? Why? If you can give us some explanation, that will be good. Why do you say that option A is correct? Did I make some mistake? Let me just recheck. For 620, no, if the wavelength is smaller, the energy will be greater. I think I'm correct. If you have explanation, you can write there and we'll get back to that. Okay, so, and this is the cause for this internal field, internal electric field E, and thus there will be a force. All right, but the problem is that this field is very complex. So physicists, they try to figure out a very efficient or a very intuitive way to say that let's just put the expression F as F external plus internal in this expression. So, and then we put the value of capital F, which is mass times acceleration, minus F internal. F internal is this. So what they say is that we'll in this whole expression, sorry about that, this whole expression that you see of F external, we'll reduce it to something else, and that is this. That we'll treat it as if we are talking about the same Newton's second law, but there's a key difference here. F is only F external, because this is the only thing that we can control. We can't control what's going on inside, right? That's what's nature or has been given, that's been given to us. We can't change that. This is a black box. So, but we can incorporate the role of F internal, right, and the mass of electron in this M effective. This is the effective mass. So the expression remains fairly simple. So this F external you can control because you know E external. This is what you are applying. M effective is something what is known as what is a property of the semiconductor itself, because it depends on the potential, which we know for most semiconductors that we encounter. A is the acceleration that we want to know. That's not so straightforward. So how do we find out this M effective? So if you see, I've been drawing, you will see everywhere this diagram being drawn, this is flat, this is not flat actually. So you see these two different cases. So this first is gallium arsenide and second one is silicon, right? You can see, so this is the valence band edge, you can see on the bottom side, and so this is the bottom side, excuse me, just a second. Yeah, so this is the bottom side, this is the top side. You can clearly see that it's not flat. This is a misleading diagram that we have been drawing on your left side. Actually they are bent. There's a curvature here on the valence band as well as the conduction band. This is for gallium arsenide, and you see the maxima of valence band is coinciding with the minima of conduction band. This is called a direct semiconductor. When these two coincide, this is E versus K, mind you, again we have talked about dispersion relation, it's coming something from that, right? This is indirect. Why indirect? Because the maxima of valence band is not coinciding with minima of conduction band. There is a, you can see there is clearly this much, they are this much apart, but Eg is given by this, right? So just keep that in mind. Silicon, this is also germanium is also indirect bandgap semiconductor. But the key thing to take away from this is that the bands are not flat, they are curved, and due to the nature that they are curved, right, due to this nature, we find try to find out an entity called the effective mass. So everything that you need to know about a semiconductor, right, what's going inside it, can be reduced to just one simple term called M effective. You just need to know this, and you can forget about the quantum mechanics or quantum physics going inside the semiconductor, right? So that's why it's so powerful, this thing. So what kind of curve we are talking about? We assume that this curve is a parabola, and this is the expression for a parabola pointing upwards, right? Y equal to cx square. C I can assume is a positive constant. This is a parabola pointing upwards. In conduction band, we talk about electrons. There are no holes here. Only the electrons can contribute to the current. So in conduction band, this means on the top half of your graph, you can see conduction band here, it's written. We talk about electrons. Just a second. Yeah, hello, go ahead. Alok, you can unmute yourself and speak or write. All right, we'll wait for Alok. In the meantime, I'll go ahead. So conduction band is, we talk about electrons in conduction band. And so you can see, so now I need to write this expression, y equal to c times x square. So what is y? Y is, you can see on the y-axis, right? And we are assuming the parabola and this, like this, c. This is, I'm assuming to be a parabola, only in this region. So I can write y-axis nothing but E minus EC. EC is I'm taking at the reference. This is your EC, what you draw. And similarly, this is your EV. And hence you see this EG as the difference between EC and EV. Okay, and C into K square. So on x-axis, you find K, the wave vector that I talked about earlier, right? And C, this constant C is given by this entity, h cut square, h cross square by 2 times effective mass. This E stands for electron, EFF is effective mass. What happens in case of holes? Holes, we talk about valence band. Valence band, we talk about holes. And we talk about this. This is the EV level. Now you can see the parabola is inverted here, right? So it will be y equal to minus cx square. Hence this E minus EV, the energy is minus h is a constant, just like C, h is another constant. Minus sign denotes that this is an inverted parabola. E minus EV is positive. E times k square. K is again on your x-axis. And I just rearrange the terms and it will come out to be EV minus E, right? H cut square over 2 times this. H stands for Hall. This is the Hall effective mass. So you can forget about Hall if it's too much. Focus only on the electrons, because holes and electrons, they are just the counterparts of each other. So no need to worry about that. And if you differentiate this expression, it's done in class also, you get this. You double differentiate this with respect to E, right? So we get this. We'll solve a problem with this, don't worry. How do we get this? But this is the expression for the electron effective mass. And similarly, you can obtain an expression for hole effective mass, which I have not written here, so that you don't get confused. Okay, but this is the expression. So now let's come back to the problem that was given to us. It says that a simplified E versus K we know is the dispersion relation, right? And we are talking about only in the conduction band, so we will only concerned with the electrons. Okay, the value of A is 20 angstroms. This is angstroms, so this is K. So K is given from minus pi by A to pi by A. We are to determine the relative effective mass. So what is the relative? Relative means something divided by their the base value. So base value in this case is m naught, mass of electron, which is 9.1 10 to the power minus 31. So we'll do that, or it's given 10 to the minus 30. So what we'll do, we'll again just we did in the last time, E minus EC is C times K square, parabola over open upwards. So E minus EC, right? And what we'll see, we are given E minus EC value at this point. It's given that here E minus EC is 0.32. So I'll write 0.32 EV equal to C times, what's the value of K? The value of K is pi by A here, pi by A squared. So the value of A, sorry, the value of C, I can simply write here as A by pi whole squared times 0.32. Note the units, this is EV times angstrom squared. Okay, so can you please provide the link? Okay, give me a second, I'll provide the link in just a second. Okay, so this is the link. I have just now shared the link for the, this is a playlist that I have created for the sessions that we are conducting here. And if you want to visit my YouTube channel, and so I'm also sharing that link. So I have shared the email ID as well as the YouTube channel, and if you want to watch the specific video, that link I've also shared. I upload these sessions on the YouTube, so for your reference you can check out at your convenience. All right, so we find the value of C, but we are interested in effective mass, right? So effective mass, this was the expression that was given to us, correct? So I just need to find del E square over del K square. That's the term that I need. So what I'll do, I'll differentiate this expression. I'll get del E by del K. C is a constant, it will come out to be 2C times K. Again take one more derivative, del square E over del K squared, it will come out to be 2 times C. So here I can write then ME effective will come out to be h cut square over del square E over del K square, which is h cut square over 2C. So this is the expression that I have gotten, h cut square over 2C, and I was interested in m star. Okay, so one more thing, this effective mass is also sometimes written as m star. So if I want to find m star by m naught, m star by m naught, this will come out to be h cut square by 2C into m naught. Okay, now you just need to put the values, and then you can get the answer. The value of h cut is 10 to the minus 34 given to us. It will be 10 to the minus 68 if we square it. The value of C is given to us here, right? A square, A is nothing but your 20 angstrom, so that will be 400. Angstrom is minus 10, so it will become minus 20, and times 0.32. EV you have to convert it into SI units, so 1.6 10 to the power minus 19, and you get a pi square over here. This is the expression. I have just put in every value. H cut we know, C we have obtained as this, m naught is given to us in the problem is 10 to the power minus 30. So I'll also write into 10 to the power minus 30 here. You solve this expression, and let me just do that. Calculator, minus 68 times pi square divide by 2 divide by 400 divide by 10 minus 20 minus 30 0.32 1.6 minus 19. I'm getting something around 0.24 something. Is there an option 0.24? Yeah, okay, so we have, so this expression you evaluate, this comes out to be something around 0.24. So you'll get option A. All right, so the lesson, so the takeaway from this question is that first thing we learn is that the bands are not flat. Even though they're shown in every diagram to be flat, they're not flat, they have a curvature associated to that. And how do we capture that physical curvature? We we condense it to a term called effective mass. And the beauty of this effective mass is that you can forget everything about the quantum mechanics that's going inside a semiconductor and just take the effective mass. So you take the classical mechanics, right? And wherever m comes, you just put m star, the effective mass, and this is the expression for the effective mass in the blue rectangle that you see. This is the expression for the effective mass. You just use this and you can just apply a classical mechanics. So you can, it's a good escape from the quantum mechanics. That's what I mean to say. The mathematics becomes much more easier, much less tedious, and much more intuitive because we have been working with classical mechanics for so long, right? So that's the about effective mass. I'll pause here for a bit and I'll wait for comments and questions if any. Alok, your hand is still raised. If you have doubts, you can ask. Okay. All right. Any comments on this? On the effective mass, any doubts? We can move forward. I'll just quickly do one more question for effective mass. So again, let's read the question. The tight binding energy dispersion relation, again this dispersion relation term comes ek. So E versus k dispersion relation for electrons in 1D array of atoms having a lattice constant area. We have talked about this term. So what it says is that, so there's a lattice, 1D lattice, this means only in one dimension, and so all the circles that you dots that you see are lattice points. So each of them, between them the distance is a, which is the lattice constant, and a total length is L. So there must be dimension to the semiconductor, right? So this length, what they're saying, is L. And if you zoom in, you'll see this picture. So if I zoom in here using a microscope, I'll see this picture. Okay, and this is the E that is given. We are required to find the effective mass. So this is a very straightforward problem. Ek is given to us and we know effective mass expression is this. As I told you, this m effective is also known as m star. Okay, just keep that in mind. So we first need to find this, only this expression. So first let's find del E by del K, that is the partial differential for this expression. Okay, I'll remind you, E naught and beta are constants. So when you differentiate them, they will go to 0. And this will become minus 2 gamma. The differential for cos is sine. Sorry, differential for cos is minus sine. So into minus sine k, and ka you will differentiate, you will get a. Remember, you differentiate with respect to k. So what I get is I get 2a gamma sine ka. Okay, I'll differentiate it again as, so this is my step 1. This is my step 2. I'll differentiate it again. So it will be 2a gamma is constant, it will come out. Sine k, the differential for sine is cos ka, and ka, the differential is a. Differentiate with respect to k. So it will come 2a square gamma cos ka. Now let's put everything, this term here. So as step 3, I'll get 1 over m star, the effective mass, that is, over h cut square, and this term comes here. So 2a square gamma cos ka. And now just rearrange the terms. It will become m star equal to h cut square over 2a square gamma cos ka. So this is the effective mass that is coming. I'll again reiterate what do we mean by effective mass. So we'll just forget about classical mechanics. So what m is for classical mechanics, the mass, right? Wherever the mass m comes, you just replace it with m star and you forget about quantum mechanics. That's the best part. So wherever m comes, f equal to ma comes, okay, make it f equal to m star a. E equal to p square by 2m, okay, very good. Make it E equal to p square by 2m star and forget about quantum mechanics. That's the best part. So m star comes out to be h cut square 2a square gamma cos a, h cut square 2a square gamma, h cut square 2a square gamma, and cos a. So this is our option B. Okay, you can see this matches here. All right, so effective mass is done more or less, and with this I think we'll rarely come across the expressions or the concepts of quantum mechanics, because everything of quantum mechanics has now been reduced to a variable called m star. All right. So that's about the quantum mechanics part as of now. If you have any doubts or comments, please feel free to ask. I'll pause a bit here, because from now onwards things will get much intuitive and much easy. You can visualize them. That's the thing. Quantum mechanics sometimes can be difficult, but now you'll find them much easier to contemplate. So I'll pause a bit over here and we'll talk about doping in a semiconductor and all those things. So any comments or questions? All right. It's better. I highly recommend you to ask, even if some doubts sound stupid. It's good to ask. If you don't know what is a lattice constant, fine. Many people don't know. I still don't. Sometimes I get confused that there are in 3D there are people talk about A, B, and C, right? I get confused. I'm very poor in visualizing stuff, so I don't get it. I repeatedly ask very simple questions to my colleagues, to my seniors, and whatnot. So it's fine. It's fine not to know. It's okay. Okay, I'll move ahead with the effective mass, and now we come to one of the most beautiful. Can you define effective mass in statements? Okay, so I'll say it like this: that effective mass for a semiconducting material absorbs, helps to forget about quantum mechanics. That's what I wrote here. Effective mass condenses all the quantum mechanics of a semiconductor into one variable. That's what it does. So all the things that you read, the overlapping of bands and everything, and Ronick Penny model, the finite barriers, the finite potentials, the overlapping wave functions, everything it just condenses the whole quantum mechanics of a semiconductor. Effective mass is a proxy, is a replacement of a mass with all the quantum mechanics effects involved. I'll write it. I'll try to define it. Effective mass is the mass of an electron or a hole. I'm not talking about hole, but it's all right, or hole, which is present inside a semiconducting material after incorporating the quantum mechanical effects. So what, in other words, you need not worry about quantum mechanics. Once you have replaced, wherever you find m in classical mechanics, you replace it with m star and just forget that quantum mechanics even exists. That's it. Okay. So now let's move to the property which has revolutionized our world around us. That the smartphones that you see, tablets, computers, the 5G and even 6G speed that you enjoy is predominantly overpowered by one semiconductor, that is silicon. And how did that come about to be? We will see. We'll see in this session. So this question says that consider a region of silicon. So this is a silicon lattice that is given to you in your diagram that you can see on your screens. Okay, and which is a perfect single crystal. Okay, so there are many things to unpack here, but let's just forget about that. So all thing you need to understand about single crystal, perfect single crystal, is that there are no defects. What do I mean by that? You see that every circle is perfect in its position. There is no gaps or anything. I mean that it's a perfect net. There are no missing silicon atoms or everything like that. It's a perfect thing. Although it doesn't exist, that's fine. It's a perfect single crystal. This means there's no defects. All silicons are present where they're supposed to be present. No extra silicon is present, right? What do we do? By some technology, we replace one of these silicons by phosphorus. You see, this silicon is not sitting here, so a blank circle is your white circle is your silicon, but you see a phosphorus sitting here. Except for phosphorus atom shown in figure 1, so only on one silicon we have a phosphorus. Note that the p atom has donated an electron to the lattice. We'll see how does it do that. So p has this, you see this is an electron that you see in black circle here. So phosphorus donated an electron, that's it, and that electron due to its some electrical forces or its own nature has come in this region denoted by the green the blue square, right? The net charge in region A and B. Region A is where phosphorus atom is present. Region B is where the electron has come. This electron has come from phosphorus. We'll see why phosphorus does that. If you recall in the last class, this was a question we spent about half an hour. What is a semiconductor, right? And we saw semiconductor, we defined it in terms of its conductivity. We saw that its conductivity ranges between metals on the right, insulators on the left. And we also saw that its conductivity can change. For instance, gallium arsenide is from -8 to 4, 10 to the power 4, 12 orders of change. That's so unrealistic. In silicon, -5 to 3. It's not possible. If you have silver, you can have conductivity only at 10 to the power 9. Nothing else is possible. You can't 10 to the power 7 or 10 to the power 11. No, it's fixed. Silicon, you can change it. How you change it? Change it by doping. This means you can make a material work. You can change the conductivity of a material as per your wish. As if you have some superhuman or you are some god, you can control everything now. That's the power of silicon doping, which we'll see now. What is doping? Formally, if you see, a formal definition of doping is that you deliberately add impurities to alter the electronic properties. There's a goal here, to alter the electronic properties. This is something like that. 24 so in the jewelry, if you have seen the advertisements or you talk to a jeweler, they'll say it's 24 karat gold. 24 karat gold is very smooth, it will break very easily. Deliberately some impurities, maybe of copper, are added to provide strength. That is, you can't that is mixing of, you are mixing some copper. A similar thing we are doing here, but on a much different scale. Okay, we'll talk about the scale later, but just understand this is the definition of doping. We add some impurities to what? To a semiconductor. In this case, we talk about silicon semiconductor. Okay, impurities to alter the electronic properties, let's say, of silicon. Silicon is an elemental semiconductor, right? So now the next question arises is that, and this is what we see here. We saw this is from the previous figure that we see. So on your white circles are the silicon atoms, and deliberately on one position I have, by some method, I have put a phosphorus there instead of silicon. This is what is called doping. Now the next question arises, what is the nature of this doping? So what do I mean by the nature of doping? Again, we'll go to our good friend periodic table. So you find silicon here in group 4, right? So what silicon has is, silicon has a valency of 4. In the last class, someone also pointed out the semiconductor has a valency of 4. Well, that's not always true. Silicon does have a valency of 4. This means it forms, in order to satisfy, it will form 4 covalent bonds with this neighboring silicon, which you can see every silicon is forming 4 bonds. Now let's look at this fellow, phosphorus. Phosphorus is valency of 3, correct? This means phosphorus, if you compare it to silicon, it has an extra electron, correct? It has an extra electron after forming 4 bonds. It has an extra electron. What happens is that when you deliberately replace a silicon with phosphorus, a phosphorus will have an extra electron. This extra electron, what it can do in some cases, it can donate. This means it can say to electron, go, I don't care about you, I am satisfied, my valency is full, I am leaving you to the world. In this case, the world means the silicon lattice. The electron will leave this phosphorus and will roam around in this lattice. Again, the Ronick Penny model and all the potential will come, but we are not concerned. So here I am simply considering a classical electron. This means the mass of this electron is m star, not m naught. M naught is 9.1 10 to the power minus 31. Here it's m star, effective mass. So I'll not bring quantum mechanics anymore. So the nature of doping, if we dope silicon with phosphorus, phosphorus will give an extra electron, hence it's called donor. Phosphorus is a donor in silicon. All right, I repeat, phosphorus is a donor in silicon. Similarly, boron is an acceptor in silicon. Am I correct in this analysis or not? You have to tell me. Or am I wrong? Do you understand why this term donor and acceptor even come into the picture? Is it clear? Because it's important. These terms will uh, keep on coming over and over again. Just a second. All right. I'll repeat that phosphorus is a donor. Okay, and which type of donor? When we dope it with phosphorus, this means when we dope group 4 elements with group 5 elements, it becomes an n type. So why n type? Because this phosphorus is a donor, so phosphorus donated an electron. This means this phosphorus will now become p plus, and this region A will become positively charged. So region A will become positive, but overall charge must remain neutral, because we have heard that electrons cannot be created or destroyed. So if it has given an electron, this means this region B must gain some negative charge due to the presence of this electron that is roaming around in the lattice. You see, this electron is not bound to any of the silicon atoms, it's free. It's in the conduction band actually, but you can assume it's to be free. So region A will gain positive charge, region B will gain negative charge. The next question arises. I took that example of gold and copper, right? I told you cannot call that doping. So the question naturally arises, what amount of doping do we call? Can we replace 10% of silicon with phosphorus? You can, but it will not be called doping, it will be alloying. We all use alloys in daily life. The stainless steel utensils that you use are an alloy of carbon and iron. If you ride a bike or a bicycle or a motorcycle, the handles that you see, they're most likely made of another quality of steel, but they may have some nickel alloyed in them or some chromium, right? And there's some many other things which you find of alloys. The bronze that you see is the bronze, which is the bronze medal that you have heard of. The bronze medal is an alloy of copper and tin. Okay, that's alloying. What do we mean by doping? Doping we do in very small quantities. We do in like parts per million. What does this mean? 10 to the power silicon atoms and only one phosphorus. Such is the range. Okay. Now, I need to ask you a question. I need to just to tell you them. You can see there's one phosphorus in 1, 2, 3, 4, 5, 6. In 36 silicon atoms, there is only one phosphorus. This is not doping actually. This is even alloying. What we do is that, so for instance, the 10 to the power 22 atoms per centimeter cube. This is silicon density, silicon atomic density, and we dope only till like 10 to the power 18 is considered very high doping. Okay, so we usually dope 10 to the power 15, 16. So you can still see, that's what I said, part per millions. Doping is measured in part per millions or part per trillions. Trillions is 10 to the power 9. 10 to the power 9 silicon, you're doping one phosphorus. That's such low levels of impurities we add. Okay, so just keep that in mind. Doping is done at a very small scale. How we do that is a completely different thing. Many technologists, it's a very complex field. People spend their research careers on that. All right, so we saw that region A in the silicon lattice, this has been doped with phosphorus. Phosphorus has an extra electron when it donates, so phosphorus becomes positively charged. So region A will become positively charged. So A has become positive, and similarly region B, since there is an electron here, it will become negative. So you'll see positive and negative. Region A is positive, region B is negative. This is the correct option. All right. Now that's good, very good. But we have all been drawing those energy band diagrams that we are seeing. So where does this energy level of this phosphorus even lie? I know this diagram. This is EC, this is EV, and the electrons can reside either here or here, because this is the forbidden energy gap. Electron cannot reside here, denoted by EG. But where does this level lie? So there must be some energy corresponding to some this fellow. Where is that? So it lies just below EC. Okay, you have to visualize it in a sense. That's what I told. So as we saw that there are many electrons available. Assume it to be phosphorus. In a silicon lattice, this is phosphorus. There are many electrons. What it can do, it can easily donate an electron, and it will come to the conduction band. It can freely roam, not freely, but it can roam inside the lattice. It is no more bound to any nucleus. So it can donate the electrons here very readily. Hence, this donor level. A good donor is one which is closely spaced to the conduction band. Okay, that's what we mean by a good donor. Yeah, near EC, correct. Just a second. Okay, so what I was saying, yeah. So a good donor will have, first of all, it can have, okay, how many electrons does a donor have depend on the doping. I already told you. Silicon has 10 to the power 22 atoms per centimeter cube, but we only dope in like 10 to the power 15 to 10 to the power 16. This is phosphorus, this is silicon. So this is the kind of doping that I'm talking about. So ED will have 10 to the power 15 or 16 atoms. We'll see how much it is, and it can donate these electrons. Okay, a good donor will have an energy level that is close to EC, so that can readily donate electrons. We'll see in the future slides at why does this come into the picture. Okay, but just for now, trust me, a donor level is very close, not very close, is closely spaced, is from the middle, it's more towards EC. Correspondingly, counterpart to this is that where is the acceptor. So I told you acceptor can be in silicon. We saw group 3 elements can be acceptors like boron. So usually the acceptor levels, for instance, I'll write here boron, they are here. What they do is that electrons cannot jump from valence band to conduction band that much easily because there's a huge gap, but they can jump from here to here, right? And the holes will be left here. Holes are nothing but absence of electrons, and they can contribute to the current. So a good acceptor level will be close to a valence band. That's the lesson that you need to take with you from this question. Okay, this red line is phosphorus. Again, I'm talking about silicon lattice, so please keep that in mind. When the semiconductor change, the dopants also change. Okay, so we see that the answer here is a little below EC, and we saw the reason why just little below EC, so that the energy difference is low enough that the electrons can readily, even at room temperature, they can get excited and go here. Remember we talked about we shine light to excite. Even at room temperature is some thermal energy. So if the donor energy level and the conduction band are close enough, then many electrons will jump at room temperature. That is, as someone correctly pointed out, T equal to 300 Kelvin. They can readily jump from in this state at ED to EC, and once they reach EC, they can contribute to the current. Okay. Now a similar question is here. So in this question, it says a bar of gallium arsenide. We have talked about gallium arsenide, semiconductor, is doped with silicon. Okay, such that silicon atoms occupy gallium and arsenic sites. So first I need to draw gallium arsenic crystal. Okay, so let me draw that. This is gallium. The red is your gallium. Okay, I should not draw it here. 1 second. Yeah, so this is my gallium, the red circles that you see, and now I'll draw the arsenic in blue. Blue is your arsenic. I'm just drawing a simplified 2D picture. In reality, it's much more complex. This is sufficient to give you the idea that I'm talking about. So as you can see, every gallium is surrounded by arsenic and vice versa. And there are, I'll again go to the red color. So there are here also. Okay, so you can just complete this whole lattice. Okay, so what it's saying is that what happens if, so I'll first write this, that this is gallium, okay, and blue was our arsenic, this is arsenic, and let's bring green color for silicon. So this is my silicon. It says, what if it occupies a gallium site? So this means, let's say from red it becomes green. That's the first case. And second case, it says in case of arsenic it becomes green. So let's say from here, what will happen? So again we refer to our periodic table for doping. Yeah, I think option A is the correct one. Let's see, let's try to figure this out. Okay, so let's consider the first case when it's being replaced in gallium. Okay, well, it says arsenic, so let's say it's being replaced in arsenic. So in here, arsenic was group 5, right? So group 5 have had already 15 electrons, right? When you deliberately replace with something with 14 electrons, it will try to gain an electron. Okay, it will try to gain an electron. This means it will try to behave like an acceptor. So silicon will try to behave like an acceptor for arsenic. This means this is a acceptor here. For group 3, note gallium is a group 3 element. Silicon has one more valency than that. So what will happen is that this has 3 electrons, satisfied with 3 electrons, but you deliberately give it 4 electrons, right? It will try to come back to 3 electrons, and thus it will donate this silicon, then it will donate 1 electron. So here it will behave like a donor. Alright, so what we see is that when we for gallium when it's for arsenic sites, and for arsenic sites it behaves like an acceptor, and acceptor means p type, right? And when it's a donor, when it's in gallium site, it's a donor, it will behave like an n type. Just a second. Yeah, so what we see is that p type for arsenic, n type for gallium, so that option comes out to be A. Silicon atoms act as p type dopants in arsenic sites and n type dopants in gallium sites. So you can see if you are on the right side of the semiconductor, just try to understand in that manner if it helps. Okay, but which will dominate? I mean, you see it's a donor as well as acceptor. That depends whether silicon, that depends on thermodynamics. So silicon wants to sit in this site or this site. So there's a lot of chemistry that's involved here in this. It's not such straightforward. All right. So that finishes our doping part. Okay, that finishes the doping part. Yeah, Parth, go ahead.
Sir, there is a question in ESC exam.
Mm-hmm.
Same question was asked, but he doesn't say that he replaced who gallium or arsenide.
Okay. Can
Sir, and the question is like this: the gallium arsenide is silicon is doped in gallium arsenide. Which type of semiconductor is this? P type or N type? So, sir, when we don't know silicon replaced either in gallium or arsenic,
yes.
then how can we determine the?
Okay. Yeah, you are correct. You are correct. From just from this knowledge, you cannot, to be honest, because you need to know whether. Okay, I'll put some hypothetical numbers. Let's say you have 10 to the 22 gallium and 10 to the power 22 arsenic atoms, right? And let's say you are only doping 10 to the power 16 silicon. Now you don't know whether 10 to the power 16 silicon will go in gallium or arsenide. It might happen that half and half is distributed. If they're distributed half and half, you'll neither get an n type nor a p type. It's intrinsic again because it's equally divided. But it so happens that silicon, it can happen that silicon will preferentially, due to the energy levels. Remember, this gallium and arsenic, it's not happening in vacuum, they're interacting with each other, so energy levels are different. Okay, I don't know, to be honest, the answer to your question what will happen. I can definitely say that the energy for silicon sitting, behaving as a donor and behaving as an acceptor, those energies can be different. And whichever has lower energy, a system always tries to go to a lower energy to become more stable. So it will then behave according to that. To be honest, I don't know the answer, but I know the logic. So if that helps, but I would have the question that you asked, right? I would have attempted cannot be determined. Okay, I would have taken that answer, cannot be determined, because I cannot determine that. I need more information, that which is lower energy, gallium silicon or gallium or arsenic silicon. until that is answered, I cannot comment. Does that answer, does it satisfy your query? I didn't answer your question, I understand that, but does that make sense to you, the explanation that I gave?
Yes.
Okay.
So then we have to read where where did this data get? So
Okay.
there is a question in previous year ESC exam, engineering service examination.
Mm-hmm. No, that's
Same,
fine. Go ahead.
so same question, sir. How do we know whether silicon replaced? How we know any element replaced any in compound? Which element replaced whom?
Mm-hmm.
Uh, from where we get idea?
So usually the first thing that you do when you don't know anything, use your internet browser, search about it. So in this case, I would search that energy of doping silicon in gallium arsenide, right? So it will give me two numbers, that what is the energy required to replace one gallium atom with silicon atom. It will also give me another data, what is the energy required to replace an arsenic atom with silicon atom. Okay, whichever energy is more, uh, is less negative, more negative, that will happen. That's what I told you, I don't know the answer to your question, but I know,
Okay, sir.
but until I get those numbers, right? If someone tell me those numbers, that okay, this energy is this much ev, minus 7 ev and minus 8 ev, okay, then I can say, okay, since the energy is lowered more for arsenic, the silicon will go in arsenic side, and then the gallium arsenide as a whole will be p type semiconductor. Okay, but until that information is given to me, I cannot comment. That's what I told you. To your answer, to your question which was asked in the, was it gate exam, you said?
ESC exam, sir.
Which exam? I'm sorry.
ESC, engineering service.
Okay, engineering service. Okay, engineering service. IES, that is right.
Yes, sir.
Okay. So I cannot say, I'll say cannot be determined, but maybe in their coursework they might have studied. I did not study this, to be honest. In my coursework,
Yes.
till now, I have not studied this as part of coursework. As part of curiosity, if someone encounters that, yeah, that's a different thing. Okay.
Okay. Thank you, sir.
Yeah, welcome. All right. So now we understand what doping means, right? Uh, Now we have seen doping. Now you understand that the doping can provide electrons. We saw that if we dope phosphorus in silicon, it can provide electrons, right? But it's only half the picture. The presence of electrons is something else, but where are electrons residing? Remember, there are energy levels throughout. We saw that, right? We have been talking about that throughout. You can see this. So these are the energy levels. This is the forbidden gap. This gap is forbidden, right? You cannot do anything here. This is forbidden for us, correct? So then these questions keep on arising, that the electrons which are there, where they go and reside. Okay, and correspondingly we have associated that for every energy level there is a probability associated with that, which is given by what we call as Fermi function. How do we arrive at Fermi function? There is again some quantum mechanics involved. We'll not go into that. It's even not even talked about in the videos, but just trust me in this, that there's some quantum mechanics involved. And using that quantum mechanics, we have come to an idea, we have come to a specific, very clear cut formula, that what is the probability of occupying an energy state. Remember, please always remember that valence band, those are energy states, different energy states. Similarly, in conduction band, there are different energy states, and in between there are energy states that cannot be occupied, right? But this is like that, those are empty chairs that are sitting there, but electron has to come and sit there. Okay, so Fermi function says that on which chair will the electron sit. There are many chairs in there. There is a room called valence band. There are millions and billions of chairs in that. Similarly, in the conduction band, there are again millions and billions, even trillions, quadrillions of chairs there, right? But which chairs will be occupied? Naturally, you know that the chairs which have the lowermost energy will be occupied first. That's what thermodynamics tells us. That's what nature dictates us to do, right? But the mathematics behind it, the physics, this quantum physics that is involved, has been reduced to a simple formula. for us, for the students to understand. Okay, so that formula is given by this Fermi function. What is Fermi function? Fermi function, I don't know how many will you, it's a probability, formally what we define is a probability distribution function. If it's a difficult word, forget about it. What does it means? It tells us the probability of finding an electron there. Okay, what do I mean by that? So it looks something like this. F is the probability of finding an electron in an energy state E. So on y-axis you see this energy E, so it rises from very low values up to some value, I don't know what is this value, right? And on the x-axis you see the probability, right? And it's related to a arbitrary number called EF. Forget about what EF is, assume it to be some energy, some level, E naught, E1, E2, I don't care, it's some energy level. It's a function of E, so you see this number E. It's also a function of temperature. We'll not talk about temperature now, it will complicate things, but just because you are being introduced, so this Fermi function tells us the probability, which I have written in words here, probability of finding an electron at any given energy level E. Obviously temperature involved, don't worry about it now. This is what Fermi function is. How it comes about? There's some quantum mechanics involved, quantum physics involved, that physicists, some good people, have worked out for us and given us this very simple and straightforward formula. Just like you remember that the good people have given us the effective mass, right? All the quantum mechanics was condensed. They just said that forget about quantum mechanics, just wherever the mass m comes in your classical mechanics, just replace m with m star or m effective and use your classical mechanics, forget about quantum mechanics. Similarly, people here said that okay, you want to know where electron is, okay, you don't need to go into quantum mechanics, just apply this formula for probability, that which electronic state is okay, which state is occupied, which chair is the electron sitting on. Just use this formula and find the probability. Obviously a total probability of finding an electron will be 1. You understand that the electron has not gone out of the lattice, it's somewhere there. All right, so using this expression, it comes out to be, as someone pointed out, it's option B. There's nothing to do, you have to, I mean, to put it very bluntly, you have to mug it up. At least for this level. For higher levels, you might want to understand how it comes, why it's not, why is exponential, why is not E square minus EF square, why is not KT square, so on. But for now, you just have to accept that this is a fact of life. Right? What it says is probability of finding an electron at any given energy level. So you can put any level E. What is EF? E is some arbitrary level, which I am going to define in this slide. EF is formally known as a Fermi level. Okay, this term here, Fermi level. So let's talk about this term here. This term will again come into your, at least in this course, and for the people who are going to work in semiconductor devices, this term will keep coming in your academic life over and over again. All right, what is Fermi level? Can anyone tell me what is a Fermi level? I've defined Fermi function for which it tells the probability. So what is a Fermi level? I'll wait for the comments. Anyone?
Where the probability is half.
Okay, very good. That's a very good starting point, Parth. Now I'll follow up with this another question. Probability of what? All right, I was waiting for the response that Vaishali has given us. Vaishali says, I'll read if you, she has written in the chat box. Fermi level is the highest energy level that an electron can occupy at the absolute zero temperature. Okay, I'll ask others, is she correct or not? Okay, I'll raise your hand if you know, if you think she's correct. Okay, so are you, raise your hand if you think Vaishali is wrong. Okay, Parth says Vaishali is wrong. Anyone else? So I am assuming all the other people here are indecisive, or I hope they are still here, not slept or anything, because I used to sleep. Okay, Vaishali is correct. Vaishali is absolute correct. Fermi level is the level. No, sorry, 1 second. What did she say? Fermi level is the. Let me read it again. Fermi level is an energy level that electron can occupy at absolute zero temperature. No, that is not correct. That's a different Fermi level we are talking about here. That's what. So in case of metals, there is also there's a Fermi level or Fermi sphere. Sorry, that is encountered. There, the Fermi sphere is the Fermi level is the highest level that an electron can occupy. That's in case of metals. In case of semiconductors, that's why this confusion arises actually. So for semiconductors, that's why I asked Parth that probability of what, right? So I'll complete that answer. Fermi level is the energy level where probability of finding an electron is zero point 0.5, is half. And I'll also say in a semiconductor. Okay, Fermi level is the energy level. It's an arbitrary energy level. Okay, an electron does not most of the times electron is not, it cannot be found, because you will see EF more of in I think in all of except for one or two cases, in hundreds of cases I have seen Fermi level to be lying directly in the directly in the EG. So you see this, we have sorry, 1 second. So we have been drawing this diagram for too long now. This is EC, forget about, sorry about the curved lines. These are straight lines actually, and this is EG, right? We have been seeing this, right? EF, you will see in many of the examples, we'll see will lie somewhere over here or here. Very rarely you will see above EC or below EV. Remember, these are the states that are allowed. So EF actually lies most of the times, it lies in the region it's not even allowed. So EF is almost you can say that with a very high degree of certainty that it's never even filled. All right. EF, what I define it as, in a semiconductor energy level, probability of finding an electron is 0.5. Okay. How do I find the probability of an electron? I know the Fermi function which you read just in the last slide. So what I'll do is that I'll say probability is 0.5. Okay. Let me put it equal to 0.5. Let me try to solve this expression. All right. So I'll try to solve this expression. It will come out to be 2 equal to 1 plus exponent of E minus EF over KT. I have just cross multiplied, okay, done nothing else. So it will come out to be exponential of E minus EF over KT equal to 1. Exponential of something is 1 only when the term is 0. So E minus EF over KT equal to 0. And we're talking about for any t, this means t is maybe, except for 0 Kelvin, this will hold. We'll go to right hand side, it will become 0. It will come out to be E equal to EF. So when the energy level is EF, so remember the definition of Fermi level, distribution function, probability of finding an electron at any given energy level E. This means probability of finding an electron is half at E equal to EF, which is the definition that I have written here on the bottom of your screen. Fermi level is the energy level, the probability of finding electron is 0.5. Again, we'll see in the future slides. I'll just request you to be patient with me. We'll see that EF very rarely lies, it's almost always lies between EC and EV in the forbidden energy gap. All right. I'll again reiterate, Fermi level is completely fictitious level in semiconductors at least. Okay, it does not physically, electron very rarely resides there in a perfect crystal. Okay, so that's Fermi level. I'll pause here if you have any doubts or comments, because sometimes it can get confusing on Fermi level. All right, I'll pause here for a bit. So the answer would be 0.5. That's needless to say. The answer is this. Any comments or questions? Vaishali, you were not wrong. I should say that. That's why in most of the times the answer it's context dependent. In this case also it was heavily context dependent, right? Okay, so we'll move forward. Now we'll solve some mathematical problems. Now I've told you that Fermi function is a mathematical function that has some quantum mechanical basics involved. And then I also told you Fermi level is a fictitious, is an imaginary level, right, where the probability is finding half. Again, it's a mathematical thing, it's not a physical thing. What Vaishali told was a physical thing, right? What I'm talking about, a Fermi level semiconductor, is an imaginary thing. It's just a level where electron doesn't even reside, to be honest. Okay, but still, we'll try to solve some problems, and we'll try to gain some intuition, right, into what it can mean. We'll try to gather some information, physical information about it. Okay, let's solve this problem. For a semiconductor at particular temperature, okay, so some temperature T is given. EF is zero point 0.2 EV below EC. Okay, this is too much information for me. I need to write it down. Sorry about that. So this is EC, this is EV, and it says EF is zero point 0.2 EV below EC. So often we denote EF by this dotted line. This is EF, your dotted line, and this gap is been given as 0.2. Very good. The probability of occupying an energy state at E equal to, okay, sorry about that, I have to move this whole diagram. Okay, so this is my EV, this is my EC, this is my EF, this is 0.2, and there is some one more energy state which I'll denote by blue. There's some one more energy state, right? Let's call this energy E1, which is given as EC plus 0.025. So this distance, this gap is 0.025 EV. This is also EV. Okay, and the probability here is being given to us as 1 into 10 to the power minus 6. So I'll write it as F of E1. What is it? 10 to the power minus 6. We are required to find the temperature T. A very straightforward problem. Okay, how I till now we have talked about only one formula that involves the probability, right? And we'll use that. I don't know anything else, to be honest. So I'll put this E as E1, simple, this as E1. Okay, F of E1 as unit 10 to the power minus 6. Okay, this is 1 over 1 plus exponential E1 minus EF. This means the gap between E1 and EF. What is this gap? You can see it's 0.025 plus 0.2. E1 minus EF, this whole gap. This is, so if you want to be more specific, I can write it E1 minus minus EC minus EF, just to be completely formal with you guys. Alright, now I'll cross multiply because I don't like this minus 6 term. So this will turn out to be 1 plus exponential E1 minus EC is given as 0.025. This is plus, it's not minus, because then only EC and EC will get cancelled and get E1 minus EF plus 0.2 over KT equal to 10 to the power 6. Alright, let's go here to solve this. So you reduce 1 from 10 to the power 6, it will not change. So I can get exponential of 0.225 over KT equal to 10 to the power 6. Again, I'm neglecting 1 in comparison 10 to the power 6. So now I need my calculator. So it will be 0.225 over KT is natural log of 10 to the power 6. That will come out to be, this is coming out to be 13.82. This is 0.225 over KT. This is K, this is T. Sorry about my handwriting. From this, T will come out to be 0.225 divided by 13.82 into K. The value of K is given as EV Kelvin inverse, which makes sense because you know this unit is EV. EV and EV must cancel, right? So that's why K is given in this unit. This is 8.62 10 to the power minus 5. let's calculate this. 0.225 divided by 13.82 divided by 8.62 into 10 to the power 5. This is coming out to be 188.9 Kelvin. Units are Kelvin, remember that please. So 188 Kelvin, 189, oh, this option is here. All right, we solved it mathematically. Given a formula, even a 10th standard student will do that. There's nothing fancy here. What do we learn from this? That's what we are more interested in. So we notice that if your energy level is higher than EF, note when E1 minus EF is positive, that means this exponential will go on increasing because this term will turn out to be positive. Exponential will increase, denominator will increase, the probability will keep on decreasing. I'll repeat, if your exponential is positive, right, the denominator will increase and the probability will keep on decreasing. If this number is negative, E1 minus EF, E minus EF is negative, this number will be smaller than 1 and this probability will be very close to 1. In other words, what I mean to say is that your graph looks something like this. You see this? For lower energies, this number is very close to 1. Why? Because the denominator is so small. However, for very large energies, when let's say E equal to 10 times EF, okay, or let's say E is greater than EF, you can neglect EF and this term will rise very rapidly. Exponential will rise and this exponential, so this will turn very close to infinity. So 1 over infinity is 0. So as you increase the energies, the probability of finding an electron decreases, comes very close to 0, which makes sense because nature says that you should fill the lower energy states first. That's what is this function. What it does is that it just satisfies your intuition, which you know that the probability of finding an electron should be high for lower energies, which makes sense. This probability function is almost 1 for lower energies. For high energies it is almost 0, and this is the same thing that we verified in this problem. What we saw is that when we find that an energy level much higher than EF, the probability is 10 to the power minus 6, very low. We'll solve some more problems and we'll again see this fact that lower the energy, higher the probability of finding an electron there, and higher the energy, lower the probability, which follows intuitively. That follows the physics behind it is based in quantum mechanics, but intuitively you have seen that happen in your life. The water will flow always along the gravity because it's lower energy. A ball thrown up will come down, right? Energy, heat, thermodynamics says that your system wants to be in the lowermost energy. Again, all those things. So this is again just an addition to all the facts, all the instances that you have been seeing around in your daily life and in some cases in your books. Okay, so let's solve one more problem related to the Fermi energy levels that we have been talking about. Okay, and yeah, let me check the time. Oh, we have half an hour, so we should be good. Okay, so what does this problem say? This problem says consider the energy level shown in the figure. So this is, again, you can see the EC, EV and everything. E1 minus EF is 0.3. So this has been given as 0.3. All the units are in EV. The probability that energy state E equal to E1 is occupied by an electron. Okay, so we want to find, this is the expression, and then we just want to find E1. Just replace E equal to E1. This is the probability. That's the only formula that we know, right? And you now intuitively know when you are above EF, right? At EF the probability is 0.5. So when you go up, the probability should be less than 0.5. In fact, it should reduce drastically. When you go down, the probability should be greater than 0.5. In fact, it should approach 1 the lower you go. We'll see that. So we'll see that what is the probability of finding electron at energy level E1. So that's fairly simple. I'll just put in all the values that I know. E1 minus EF is given as 0.3 EV, right? KT has been given as 0.025. Note, this is EV, this is also EV, so EV and EV cancel. Okay, so I'll use my calculator again. So 0.3 by 0.025 is coming out to be 12. Exponential of 12, that should be a huge number. Okay, That's coming out to be, 1 second, that's coming out to be 1.63 10 to the power 5. Okay, so it's coming out to be 1 divided by 1.63 into 10 to the power 5. I'll neglect 1 because it's much smaller than this number, so this approximately turns out to be 6.14 into 10 to the power minus 6. And you see that the probability at EF it's 0.5. As we go up, the probability should reduce. It is reducing. It's minus 6 in the last problem also. Remember that the probability was in minus 6 if I'm not mistaken. Yeah, it's minus 6. So you see that. So as we go up, the probability reduces drastically. Why drastically? It's an exponential function. Exponential will have that effect. Okay. So for F E1 is 6.14 10 to the power minus 6. So we know that now the option is C. But we'll also calculate the second part, which is here. We want to find when E equal to E2 is empty. Now intuitively you know that E2, the probability of E2 of filling should be very high because it's below EF. But here we want to find E equal to E2 is empty. How do we do that? So first let's find out this. And probability E2 is empty is 1 minus E2 is filled. Because total probability must be 1. Correct? So either E2 is empty, E2 is filled. That sum should be 1. And we want to find what is E2, that when E2 is empty, that is 1 minus E2 is filled. So that is 1 minus f of E2, right? So we just need to find this answer. So 1 minus f of E2 is probability that E2 is empty. So for that we need to find f of E2. So let's do that. F of E2, 1 plus exponential of E2 minus EF over KT Okay, so let me make our lives a bit simpler because it's going to take too much space then. Yeah, so f of E2, I know the formula for that. I'll put it here. 1 minus 1 plus exponential E2 minus EF upon KT. Take the LCM and you will get as exponential of E2 minus EF upon KT upon 1 plus exponential of E2 minus EF upon KT. So I just need to find out this exponential. So let me find that out. E2 minus EF, right? This was given as 0.3. So what is this? This is 1.12 minus 0.3, and that is 1.12 minus 0.3 is 0.82. So this is 0.82. So E2 minus EF is minus 0.82. So I'll write this expression here. So minus 0.82 divided by 0.025, which is KT. Remember that. That comes out to be minus 32.8. So that's exponential of minus 33. And that number turns out to be 5.7 10 to the power minus 15. This is just mathematics. I am just skipping writing some steps, but I am explaining them. Okay. So this is that 10 to the power minus 50 is nothing in comparison to 1. So I can approximate it as 5.7 10 to the power minus 15. Again, which is the option C that you see here. So what do we learn is that the probability of finding E2 empty is I mean ridiculously close to 0. This means E2 alone, for all practical purposes, you can assume E2 to be filled. And if you recall, 1.1 is the band gap for silicon. Okay, and this is the valence band that is being denoted here. And this is what we have been talking about. That valence band is most likely to be filled, and at 0 Kelvin it's completely filled. It's fully filled. But here, since we are we are talking about some finite temperature at T. In fact, here T equal to 300 Kelvin. I know this because when you put the value of K, Boltzmann constant, you'll get find T equal to 300 Kelvin. Just try doing that. Okay, so find that at room temperature, valence band being empty, probability of E2 is empty, is very close to 0, right? It's very not 0, very close to 0. Again, the probability comes because it was derived from quantum mechanics, so please understand that, please keep that in mind. So the absoluteness will never come, but the probability, our intuition is satisfied that valence band is more or less filled, which it shows, it's 10 to the minus 15. Its probability of being empty is very close to 0, which makes sense. And as you go up and up, you can see the probability of finding an electron keep on decreasing. All right. So again, I'll take a pause here because we have been talking, we have solved 3 or 4 questions on Fermi function. I'll take a pause here and I'll wait for your comments or questions, if any. So the pace, I noticed that in my last class I've been going a bit too fast near the end in order to complete the questions. So it's quite possible that I might not touch all the questions for this assignment, but that's fine. I'll still upload all the solutions to the I'll upload a PDF file of this PPT and you can check that out, the solutions there if you want. I'll try to complete all of them, yes, but and not at the cost of skipping some concepts. That's the idea. Okay, let's move ahead. So next question says, assume that the Fermi level is near valence band. Which of the following is true? So I'll draw that. EC, EV, near the valence band. So let's this is EF. Which of the following is true? Okay, again I know only one expression, which is f of E is 1 over 1 plus exponential of E minus EF over KT. Now if you notice carefully, if the EF were in middle, right, if the EF were, let's say, this large dashed line, EF, we call it intrinsic. If it were here, the probability of finding an electron here is half. This means you go lower, the probability keeps on increasing, but we are already on the lower side. The original EF, the given EF is here. This means that the probability of finding electron here is half. Correct? What that, in other terms, that means that we'll see in terms of expressions that, but you just have to trust me in this case, that EF, this means has more holes. That's what that means, because when EF is close to the valence band, originally EF for an intrinsic semiconductor is directly at the middle. When you dope it p-type, it keeps moving towards the valence band side. It keeps moving down. Okay, and that means it's behaving like a p-type. We are doping it p-type. If it tries to move up, then we are doping it n-type, and we are doping it p-type. This means the number of holes are greater than number of electrons. That's what p-type means. And also P is greater than Ni. These terms will make more sense in a bit, but we'll revisit this question again. But for now, the answer is this. Because the Fermi level is pulled down, then E minus EF, if you see, the probability of finding an electron, right, in this side will be more. The probability of finding electron will keep on reducing because you're far away from EF than you were earlier. The probability of finding electron will be even lower. The probability of finding a hole will be even more. That's why P greater than N. And so probability of finding a hole is larger than the normal level. It's denoted by Ni. We'll see that again. Just mathematically we'll see that again. Okay. So mathematically we are seeing this now. The silicon is at T equal to 300 Kelvin, which is the room temperature, is doped with boron. Now I want you to recall your periodic table. So boron was group 3. In group 3 we saw it was p-type. So this means this will form a p-type semiconductor. Boron is a p-type impurity or an acceptor impurity, and hence the concentration of holes is given. If it were the other side, concentration of electrons would have been given. Okay, the position of Fermi level with respect to EC is, okay, there are many terms that are involved here. So if you visit the lecture slides from Professor Naresh, you'll find these two expressions where N is the number of electrons in the conduction band, P is the number of holes in the valence band. Okay, the vice versa is usually not seen. The electrons we only talk about in the conduction band, and the holes we only talk about in the valence band. Where NC and NV are two constant, how do you arrive at these constants? Again, you see this term Mn star and Mp star. These are the effective masses. So they have their basis in quantum mechanics, right? But for our purposes, as for the people who want to learn the electronics of semiconductor devices, right, we don't care about that. We only care about that Nc and Nv are some constants, right? And using these constants, we can arrive. Nc and Nv are also constants. Nc and Nv are constants, and Ef is usually the Fermi level that is being dictated by the doping that we do, right? And so electrons and holes can be determined using this formula. Okay, just a second. Okay, so now it says the position of Fermi level with respect to EC is, so number of holes is given, so this is the expression that we'll use. Okay, NV is also given, so this is actually P naught, this is N naught. So P naught is given NV exponential EF minus EV over KT. So let me use this expression. P naught is given 5 into 10 to the power 15 equal to NV. NV is given 1.04 10 to the power 19 exponential of EV minus EF over KT, right? Right. So from this I can find EV minus EF equal to KT, log to the base E. I'm just rearranging the terms. You can take this term on this side, so it will be 5 divided by 1.04, that will be 4.81 into 10 to the power minus 4. Okay, and we take a natural log of that, multiply it with by KT, which is 0.025 EV. So this is coming out to be EV minus EF is coming out to be minus 0.191 EV. Remember, minus 0.191, this means EV is below EF, which I have been telling you, which is often the case. This is EC, this is EV. EV is 0.19 below EF, so this is 0.191 EV. This is your EF. Remember, this is silicon, so silicon we know band gap is 1.1 EV. Okay, and what we wanted was position of Fermi level with respect to EC. We wanted to know this. What is this? This we can easily find. So EC minus EF, we can say that this implies EC minus EF is 1.1 minus 0.191, which will come out to be reduce 0.19, this will be 0.91 something, close to 0.91 EV. So EC minus EF is 0.91 EV. Any option? Yeah, close enough. I approximated a bit. I assumed KT to be 25 millilect 0.025 EV, and it's fine. Just I was telling you the how to approach these problems. So that's what's happening. And again, you see, remember, boron is a p type, an acceptor type, and we find that EF, rather than sitting in the middle of an intrinsic silicon, it shifted very much towards the valence band. And that's what I was telling in the last slide to you, right? Remember the last question, that if the Fermi level is near the valence band, that means it's a p-type semiconductor. So this means that's what this was written here. It's a p-type semiconductor, and for a p-type semiconductor, we saw here p is 5 into 10 to the power 15, right? And Ni was 10 to the power 10. Okay, so you see from the previous case, we saw p was 10 to the power 15, n you calculated come out to 10 to the power 5, Ni is 10 to the power 10. So this option 10 to the power 15 is greater than 10 to the power 5, which is true, and 10 to the power 15 is also greater than 10 to the power 10. So that's what I told you intuitively here, that why the band will shift down. We saw that through the probability function. In this case, we saw it numerically. This is a more rigorous approach actually, but sometimes sometimes the examiners might just want you to compare two graphs, how to do that. That's why I solved that question first, which did not have any numbers, just to give an idea, just to give an intuition as to how to work. All right, so right now a major thing is you must remember that all these formula that I have written here, and not P naught, NC, NV, This is applicable only for non-degenerate semiconductor. Okay, now the next question arises, what is a non-degenerate semiconductor? So I'll draw this diagram again. EC, EV, EF can be anywhere in between. EF cannot be too close. So remember, this is some EF1 and EF2. So this gap and this gap has to be greater than 3 kT. I told you that all the formula that you are seeing on your screen had some quantum mechanical basis, right? And they had some assumptions involved too. One of the assumptions was that this gap must be at least 3 kT. K is a Boltzmann constant, T is the temperature. So kT is, you can see, 0.025 eV. So this gap has to be at least 0.075 eV. Please remember that the question might be asked where this gap is less than 0.075, and then all this formula, all this analysis is useless. Okay, then we just have to go the quantum mechanical way. There are some other formulas, we'll not go into that, but just keep into account what do you mean by non-degenerate semiconductor. Non-degenerate semiconductor is this is a non-degenerate semiconductor. Please remember that. Okay, and all the formula that you're seeing on screen are applicable only to non-degenerate semiconductors. All right, any comments, questions? All right, we have 10 minutes. I'll just go through a couple more problems. So this is a good problem. So it says that silicon wafer, so we have a silicon wafer, and I'll again assume this is the silicon lattice that we have. This is silicon lattice, and we have doped with p-type. So Na, you see, A stands for acceptor, so it is Na is 10 to the power 15. Remember, silicon is 10 to the power 22 cm minus 3, the silicon density, and Na is 10 to the power 15. I told you it's very small, parts per million. It's not even parts per million, it's 10 to the power minus 7, close to parts per million. That's fine. At T equal to 0 Kelvin, the equilibrium and hole concentrations are. So again, I'll draw that I'll repeat that diagram. EC, EV, and this is an acceptor, so we know EF will lie somewhere here. And we know that some electrons can jump from here to here, and thus they will leave behind holes, and these holes will contribute to the current, can contribute to the current. Now the question arises, at T equal to, what makes the electrons jump from this level to this level? Correct? That's the question. What makes an electron jump from here to here? It's the thermal energy. Or you can also shine some light. We saw in the first problem today that you shine a photon, and a photon can excite this electron from here to here or from here to here depending on the energy of the photon. But usually this gap is fairly small, such that even at room temperature, some of the electrons will jump from here to here. But at room temperature, remember, at 0 Kelvin, there is no thermal energy. And are you shining any light? There is no photon, there is no energy. So there is nothing. The electrons can jump from here to here, but there is no energy. Hence, there will be no electrons in this, and thus consequently there will be no holes here. Okay, so there will be n equal to 0, p0 equal to 0. Then you will say, okay, fine, the doping is not working, but we always have intrinsic electrons, Ni and Pi, which we know, which is, an electron is 1.5 10 to the power 10 at room temperature. Again, remember, at room temperature. Where do these electrons and holes come from? They come from the breaking of the bonds, silicon bonds. And why do those silicon bonds break? Remember, these are the bonds that which are here. They break because of thermal energy. Room temperature 300 Kelvin, these bonds have some energy. These bonds can break due to that energy. But at T equal to 0 Kelvin, there is no energy at all. It's absolutely frozen. So there will be no electron or holes because the dopants cannot be ionized. At T equal to 0, dopants are not ionized. This is the first reason. And second, no intrinsic, because again, no thermal energy. So the whole point is that at T equal to 0 Kelvin, there is no thermal energy. There cannot be any electrons or holes even in the semiconductor. Hence, the answer would be this. P equal to 0 and N equal to 0. All right. I'll increase the temperature, same problem. Now I increase the temperature. Now what can happen is that, remember, silicon lattice, one of them is p type, so let's say this is a boron, rest of them are silicon. Okay, now what can happen at equal to 300 Kelvin, again I'll draw the same diagram, EC, EV, EF. Now an electron can jump because at 300 Kelvin there is some energy that this electron can gain. It can go here, leave behind a hole, and thus this hole can contribute to the current, called the current J. Okay, how much? And again we'll assume that all p type are ionized at T equal to 300 Kelvin. You say, how do you know it's ionized at 300 Kelvin? Usually the way we choose dopants, I told you we chose the dopants that EF should be close enough, and again we choose dopants that they are usually ionized at room temperature, because all the devices that we use are mobile phones. They operate at on or about room temperature. Temperature can increase, and in cold areas temperature does decrease, but it's a safe side that they ionize at much lower temperatures. So all the boron that is here, they can gain an electron then, and thus a huge number of holes will be generated. How many holes? 10 to the power 15 holes can be generated. So number of holes equal to Na at 300 Kelvin. So P will be equal to 10 to the power 15 Cm minus 3. What about N? You know the law of mass action. Using that you can find N naught equal to Ni square by P naught. Ni square is 10 to the Ni is 10 to the power 10 given in the problem. Divide by 10 to the power 15 and you will get 10 to the power 5 Cm minus 3. So P naught we find at 10 to the power 15 Cm minus 3, N naught at 10 to the power 5 Cm minus 3, which happens to be 15 and 5, this option. I'll reiterate, at 0 Kelvin there was no thermal energy to excite the electrons here in this dopant level, this boron. This is for boron, right? In the last slide also I'll write this is boron. This is not happening at all. Here it's happening because there is a thermal energy, okay, at room temperature. That's why you find P equal to 10 to the power 15 and consequently N equal to 10 to the power 5. Okay, one more chapter to this because all these three concepts are related. So now it says that temperature increases 10 to the power 5 10 to the power, to 5 Kelvin to 700 Kelvin. We know at 5 Kelvin there will be barely any very few ionization. I told you T equal to 0 K, no ionization. At T equal to 5K, very few ionization. At let's say T equal to 300K, full ionization. Whose ionization I'm talking about? The dopants. So remember we are doping boron. Boron will become P type. So B plus, sorry, it's an acceptor. So it will become B minus. It will gain an electron from silicon. If it's P type, like phosphorus, it will become P plus. It will donate an electron. We saw this how they gain and donate an electron, right? There were energy levels involved, like this was EC, this was EV, this was phosphorus, right? This was boron. So electrons can go here or from here to here. We saw that at 300 Kelvin will assume that all the borons have the capacity to gain electrons. Similarly at 300 Kelvin, if it's a P type, it's an N type, all the phosphorus atoms can donate an electron and thus become positively charged. What happens when you even increase the temperature? Let's see this plot. This is again from the lecture slides and from the Streetman Banerjee book that the Professor Naresh has been referring to. So you see at very low temperatures, you see less than 100, you see this temperature, assume this to be 5 Kelvin. At 5 Kelvin, see very few have been ionized, only 10 to the power 12. Extrinsic, here it's full ionization. Full ionization. And you see it remains constant because all that is supposed to be ionized has been ionized, and this ionization was complete around at 100 Kelvin. See this? It's around 100 Kelvin. So at 100 Kelvin everything was ionized. At 5 Kelvin very few was ionized, right? At 300 Kelvin, full ionization. You see T equal to 300 is full ionization. And at 500 or 450 or something, you see it's complete ionization. What happens after 500? You see there are silicon bonds that are there. They start to break. Okay. Then the intrinsic nature takes over. Okay. We usually don't want to operate in this regime because we don't know how it will behave. Here we know whatever we are doping, right, that much only will be the concentration of electrons or holes. If you're doping in n-type, then concentration of electrons, let's say. Okay, here it's, you can see it changes very rapidly. Here it's constant. So when you want to make good devices, right, very more often than not we operate in extrinsic regime, and you see the temperature range that we are getting from 100 Kelvin to approximately